So today I'm going to show you how to find a generalized continued fraction for the square root of z, specifically the principal value, and it's valid for almost all complex numbers z. Now if you don't know what continued fractions are, here's a good example with the golden ratio, 1 plus square root of 5 all over 2. It satisfies the golden ratio is 1 plus its reciprocal. Now you see we have this thing here and here, so we can just replace it again with 1 plus 1 over 5, and basically you can infinitely nest this, and then you have 1 plus 1 over 1 plus 1 over 1, and so on and so forth, and this converges to the irrational value that is the golden ratio. Now these can also be finite, but those are specifically for rational numbers. Rational numbers always have finite continued fractions. Generalized continued fractions are specifically with different numerators, while simple continued fractions have only ones. So with this one, we're going to start with the factorization of z minus 1 in the complex numbers. Again, specifically talking about the principal square root. If you want the other one, you just put a minus sign in front. So this can be rewritten as the square root of z squared minus 1 squared. Then with difference of squares, we can factor it as the square root of z plus 1 times the square root of z minus 1. Now we're going to divide by the square root of z plus 1 on both sides, and we're going to get the square root of z minus 1 is equal to z minus 1 over the square root of z plus 1. Now we can rewrite this denominator on the right side a little bit so that we get z minus 1 over 2 plus square root of z minus 1, right? We replace the 1 with a 2 minus 1. Now you see we have this over here and this over here. So that means that we can, again, basically infinitely nest this inwards, and we're going to get the square root of z minus 1 is equal to z minus 1 over 2 plus z minus 1 over 2, and so on and so forth. And then just add 1 back on both sides, and we're going to get the square root of z is equal to 1 plus z minus 1 over 2 plus z minus 1 over 2, and so on. Now I'm going to use a special notation for continued fractions that Gauss used, which I like. It's shown on screen here. Basically like sigma notation, where it's this big operator index from k is equal from 1 to infinity. And so for our specific case here, we're going to have square root of z is equal to 1 plus big K, for k is equal from 1 to infinity, of z minus 1 over 2. This doesn't depend on k here, all the nested fractions. But anyways, so this is what we have. But now, this doesn't actually converge for all values, and we want to figure out exactly for which complex numbers it converges. So I'm showing here on screen the definition, kind of like limit of partial sums for summation, where these are the conditions for when the infinite continued fraction converges to some finite constant. So instead of partial sums, what we have is this xn is equal to a sub n over b sub n, right? This is what's called the nth convergent, which is basically if you cut off the infinite continued fraction at k is equal to n, and then you take that itself. So if we look at some of the first convergence, we have xo, which is ao over bo. It's just equal to the initial term bo. Then we have x1 is equal to a1 over b1. We add the first rational term. So we have bo b0 plus a1 over b1, and getting them with common denominator, you're going to get b1 b0 plus a1. This is all over b1. With a similar method, you will see that the second convergent will be equal to b2 times b1 b0 plus a1 and then plus a2b0 all over b2 b1 plus a2. Now in general, for the nth convergent, we will have a recurrence for each of these, the numerator and the denominator over here. So this is going to be capital A of n over b over n, where we have a sub n, capital A sub n, is equal to little a sub n times capital A sub n minus 1. Or sorry, we have to start with b here. It's b sub n times capital A n minus 1 plus a sub n times capital A n minus 2. And then b sub n is equal to little b sub n times capital B sub n minus 1 plus, sorry, this one is supposed to be an an right here, an, and then times capital B sub n minus 2. And the initial conditions for each of these are that we have a minus 1 is equal to 1, and then a0 is equal to b0, the first term. Then we have capital B minus 1. This is equal to 0, and capital B0 is equal to 1. Okay, now for our case over here, what we have with our terms, right? So we have this one. It's nice because an and bn, these guys are constant, right? It's always just z minus 1 over 2 plus z minus 1 over 2 and so on. So we're not going to have any like hard recurrences to solve. We're going to have, for ours, it's going to be an is equal to 2 times an minus 1 plus z minus 1 times an minus 2. And then we have bn is equal to basically the same recurrence. The only thing that differs is the initial conditions, right? So the initial conditions of a minus 1 is equal to 1, a0 is equal to 1, then we have b minus 1, 0, and b0 is equal to 1. Now, with the way to solve these, you could use any kind of method that you might be familiar with, like generating functions or characteristic polynomials. One that I considered was that I've showed how to solve using characteristic polynomials in something for the Fibonacci sequence, if you haven't seen it before. But what we're going to get is, if when you solve this, you're going to get a sub n is equal to 1 over 2 times 1 plus root z to the n plus 1 plus 1 minus root z to the n plus 1, and b sub n is going to be 1 over 2 square root of z times 1 plus root z to the n plus 1 minus 1 minus square root of z to the n plus 1. Okay, so now we can consider the limit of the nth convergent. The limit as n approaches infinity, an over bn so after simplifying, we're going to get the square root of z out front here. Then we're going to have 1 plus square root of z times n plus 1 plus 1 minus square root of z to the n plus 1. And this is going to be all over 1 plus square root of z to the n plus 1 minus 1 minus square root of z to the n plus 1. Now what I'm going to do is I'm going to factor out the square root of z and then separate this fraction by addition of their numerators, and then basically multiply both sides, both numerator and denominators, by the reciprocal of 1 plus square root of z to the n plus 1. This is just to simplify things. So we're going to get square root of z out in front, limit as n approaches infinity of, so 1 plus square root of z to the n plus 1 divided by the same thing. We're going to have 1 over 1 minus square root of z over 1 plus square root of z all to the n plus 1, and then plus, then we're going to have 1 minus square root of z over 1 plus square root of z to the n plus 1 all over same denominator, 1 minus square root of z over 1 plus square root of z to the n plus 1. So this is our expression here. Now, if we want to get square root of z, we want this to approach 1, which basically, if you see, if this stuff goes to 0, we're going to have 1 over 1 minus 0, that's just 1, and then plus 0 over 1 minus 0, which is 0. So that means that we want 1 minus square root of z over 1 plus square root of z to the n plus 1 to approach 0. Now, for any general complex number over here, it could be n or n plus 1, right? Both things approach infinity. If we have the limit as n approaches infinity, I'm going to call this complex number w. We have w to the n. So using polar form, we can express this as limit as n approaches infinity of the modulus to the n times e to the I n, the argument of w, right? And so this part over here is bounded, right? It's just going to be, it's always going to keep circling around the unit circle, but it's something that's bounded, all right? So the only thing that could shoot off to infinity is the modulus here, and this will only go to 0. This will only go to 0 if it is less than 1, okay? So that means that for our original limit here, we have that it will approach the square root of z so long as we have 1 minus square root of z over 1 plus square root of z absolute value is less than 1. Alright, now we're going to want to solve this inequality at the end a little bit more to get a better picture of what complex numbers actually work. So I'm going to first, just to simplify this, we're going to use the rectangular form for square root of z. We're just going to let square root of z to be equal to a plus bi. So we have a is the real part and b is the imaginary part. So we're going to get 1 minus a minus bi over 1 plus a plus bi. Absolute value, this has to be less than 1, and then using the definition of modulus, basically the distance, right, from the origin, is just going to be the square root of 1 minus a squared plus b squared all over 1 plus a squared plus b squared. And this has to be less than 1. Then we can, this is 1 squared here. We can square both sides and move this over to the other side. So we're going to have 1 minus a all squared plus b squared less than 1 plus a squared plus b squared. Now if we expand this side, we're going to get a squared minus 2a plus 1 plus b squared is less than a squared plus 2a plus 1 plus b squared. Now we see here this stuff is going to cancel out. So we're just left with the minus 2a is less than 2a, which just basically we have 4a. 4a is greater than 0, or just a is greater than 0, which we know is the real part of the square root of z. This has to be greater than 0. Now, I'm going to do another substitution here. Let's let square root of z to be equal to w. So we're going to have the real part of w to be greater than 0. So w is just any other ordinary complex number. So geometrically, we can already intuit what the solution is going to be here. If we look at the complex plane, right, when is the real part going to be greater than 0? Well, that's basically, I'm going to try it in red. It's basically this entire region over here, all right? And if we want to express this by argument or by the angle, we see that we will have basically this entire area, so it's up till pi over 2 and minus pi over 2, right? Not including 0, not including anything directly on the imaginary axis. So basically what we're going to have is that the absolute value of the argument of w is less than pi over 2. Now we know that the argument of for square root, right, square root of z, at least for square roots here in the principal range, we will have that this argument by de Moivre's theorem. If you don't know about that, I made a video on that too. But basically it's just messing with exponentials and then distributing this factor into the polar form. We have the square root of z, that's 1/2, so we're going to have the absolute value of the argument of z over 2 for the square root of z, basically. And this has to be less than pi over 2. Then all you have to do is cancel this, and so we get the absolute value of the argument of z is less than pi. Now, what is this exactly? Again, the argument here is the principal angle, like nothing plus or minus 2 pi n, you know that. But so for the principal angle we're talking about here, we are going to have that this basically includes all complex numbers except 0 and all the negative reals, right? Or all the, let's be specific, all the non-positive reals, okay? Right? Because then you're going to see, you're going to have this the real part that is going to be 0, right? It's going to be exclusively imaginary, right? Because we have the square root of like minus x, which is equal to, right, the principal square root of x times I. Real part is 0. And then 0, obviously, that's also going to have real part and imaginary part 0. So here's the deal. It seems like this works exclusively for the argument of z, absolute value, strictly less than pi. However, we also have that this will actually work for 0, but we have to start from the beginning. If we have z is equal to 0, we're going to have the 0th convergent is going to be equal to 1 minus 1/2, which is equal to 1/2. Then we have x1 is equal to 1 minus 1 over 2 minus 1 over 2, which after simplification becomes 1 over 3. And in general, we have the nth convergent is equal to 1 over n plus 1. And you know that this approaches 0, which is the square root of 0, as n approaches infinity. So, overall, we have that square root of z is equal to this continued fraction, 1 plus big K. K is equal from 1 to infinity of z minus 1 over 2, so long as the absolute value of the argument of the complex number z strictly less than pi, or z is equal to 0. Alright, so I hope you enjoyed this video. I hope you found it insightful. Good introduction to continued fractions. The next video is also going to be about continued fractions. I kind of just did this as a setup. and I will see you in the next one. Goodbye.